So let's keep going. And let's actually use this stuff that we've been kind of learning. And so remember, most of this we're doing in order to calculate the area. And so suppose we have the following function. So I have x cubed minus 2x squared plus 2 here in blue. And so what we're going to want to do is let's calculate the area of the curve between 0 and 2, right? So I want to say the area under the curve between 0 and 2. So how do we do this? So here I have, let me see. So I want to calculate this area, right? So this is not necessarily something easy to do. So how can we do this? Well, like think about it for a second. What's a good way? Well, one way we can do this is to cut this up into little rectangles. So let's actually do this. So let me remove this and let me cut this up into rectangles. Let me do orange. And we're going to cut this up into halves. So let me look at this line here, look at this line here, and look at this line here. And let's look at this rectangle plus this rectangle plus this rectangle and then this rectangle, right? We're going to have to keep our rectangles the same for all the cases, right? Since we always started here from the left, I should make all of them from the left. And so what do I have? So here I have f of 0 times, this distance is 1/2, right? Times 1/2 plus f of 1 divided by 2. So it's the same. The distance here is also 1/2 plus f of 2 over 2 plus f of 3. Why am I doing 1? Oh, okay. Now we'll do this. 1 over 2, sorry. 1, 3 over 2 over 2. Yeah? And so this we can write in summation notation. So here I'm taking my I from 0 to 3. And if you can think of this as over 2, basically I have f of I over 2, 0, 1, 2 over 2, 3 over 2. So I over 2 divided by 2. So this is what we have. This divided by 2, I'm going to rewrite actually as change in x, right? This is what was our change. So in this case, this was 1/2. So what do we have? We have, so f of 0 is 2 times 1/2 plus, now this you would need a calculator, right? So f of 1/2 is 13 over, divided by 2 is 13 over 8. The next one is 1, and the next one is 7/8. And then these are all times 1/2. So this ends up being 11 over 4, which is roughly 2.75. Okay, but as we see, there's like, here we added too much, right? And in this case, we didn't add enough, right? In order to compensate the ones on the left. So one way we can get around this is to make these rectangles smaller. So we can actually make them smaller, right? So let's cut it into 10 portions, yeah? So let me remove this stuff. And let's cut it into 10 portions. So here would be the little lines, right? Each one of these is 0.1, 2, 3, 4. Yeah, each line is one little rectangle. So I'm not going to draw them out. But if you do the same thing, I guess we should do times 20. No, I want 10. So we'll do every 2. So we'll have one here. We'll have one here. We'll have one there. We'll have one there. We'll have one there. We have one. So it's kind of like a bouncy pattern. There. And then this one there. This one there. This one there. Yeah, and that's 2. And so notice how each one of these, so if I take these lines down, each one of these are going to give me a little rectangle. And these rectangles are basically the exact same rectangles as we saw in this first case, right? Except our summation is going to be different, right? So here, instead of I divided by 2, we're going to take I divided by 5. Right? So here I have my summation. We'll start off with 0 because we have f0. So 0 divided by 5. Sorry, I divided by 5. And here we have our change of x as well. Our change of x is different. And how many of these do we have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So what do we have? So if I were to do this summation, delta x is a constant, so I can take it out on the side. So what do I have? I have 2 plus 241 over 125 plus 218 over 125 plus 187 over 125 plus 154. You don't have to write this down if you don't want to. I'm writing very much not neat in this case. Plus 1 plus 106 over 125 plus 103 over 125 plus 122 over 122.5 plus 169 over 125. And all of this times our change in x, which is 1/5. So what does this give us? This gives us 67 over 25, which is roughly 2.68. So notice how each one of these I made a little bit smaller, right? So I'm calculating less of an error. So this number should be closer to what the area is. But we still don't have an exact thing. What we can do is notice how 2.75, then we get 2.68. And actually what we're going to end up finding is that the area should probably be around 8/3, which is 2.6666 ... In essence, what we're trying to calculate is the following, right? So I have some change. I'm going from some point I is equal to 0. Xi, so these xi's have been I over some number, right? Yeah, I over some number. I'll just make this C, I guess. And change in x. And we've basically been doing little rectangles. But we can also change kind of how we do our rectangles, right? We can also look at our rectangles from the right-hand side. Here, remember, I'll do the bigger example. So if I were to do 1/2, what I can do is I can look at this rectangle, and then this rectangle, and then this rectangle, and then this was horrible line, this rectangle, right? And so I can look at the right-hand sides of our rectangles instead of looking at the functions from the left. Let me draw the left one on top of it. This was our original one. So our original one looked like this, looked like this, looked like this, looked like that. So notice how in some cases we underestimate or overestimate depending on which one we're in. But in both cases, we're over or underestimating. So the right-hand side is it's basically the same, except here we have an I plus 1. We look at this coordinate on the right instead of this coordinate here on the left. The change of x here is not changing. We're still starting from the same number and still ending at the same number. And so, for example, if we do it from our previous example, in this case, this is not always the case, but in our case, it turned out that we have the same thing. And this is because of this, that f of 2 is equal to f of 0 is equal to 2. So this is not always the case, but for us, these two values end up being the same. Okay, so how does that kind of help us? So now we're going to look at a different function. What time is it? How long has it been? It's been 25. You did 5, so 30. 10, 20 more minutes. Okay. So let's look at a different function. And let's be a little more precise with these rectangles, right? So we haven't been too precise. And like we said, we're trying to calculate the area, right? So let's talk about these intervals here. And let's be, I said this 5 million times, more precise. Don't listen to me. Well, no, listen. Okay, I didn't say anything. But happy day. I'm going to draw a little stick figure with a happy face. Because, yeah. Anyway, we're going to look at this function. Moving on. F to the x is equal to x to the 5 minus 6x squared minus x plus 1. Let's look at what this function looks like. And maybe I should rewrite this here up top so you can kind of see it. I don't know why I let the notes do this, but normally it's not this bad. Minus x plus 1. Okay, and so we're talking about these intervals, right? And so we're going to want to break these intervals into what's called partitions. So if I have some closed interval a to b, a partition of this interval is some way of breaking up the numbers into little subintervals. So here we get little subintervals. And so you can basically think of this as like, say if I'm going from 0 to, I don't know, 1.5, I can break this up into little portions where I say, okay, I'm going to take this line and this line and this line and this line, and that's it. And then these will give me my interval. So this will be A, this will be x1, this is x2, this is x3, this is x4, and then this is x5, which is our B. And so here you can notice that they're all in order, right? What x0 is less than x1, is less than x2, x3, x4, x5. And then these are each one of these are giving us little intervals, right? So each one of these is its own little interval. If the intervals are all the same size, so in this case this is not intervals of the same size. Let me delete this. If our intervals are the same size, so what? I guess if I'm doing 1/2, 1.5, if I do 1 and 0.5 and 0, notice how these are all the same distance, yeah? They're all 1/2 distance for the intervals. If they're all the same, then we say that the partition is regular. And in this case, they're all going to have the same size, and our size is going to be b minus a over n. So let's try this quickly. We have 1.5 minus a is 0 divided by n. So we have 0, 1, 2, 3. So divided by 3. So we have 1.5 divided by 3. This is just 0.5. And notice how, in fact, our intervals here are exactly 1/2. So this is a regular interval. So let's look at some examples, yeah? We're going to let a be 2. We let b equal to 5. And here's two different partitions, right? So I have 2, 2.1, 3, 4.2, 4.5, 4.51, 5. And then I also have 2, 3, 4, 5. So these are my intervals. My partition. And these are going to give me different subintervals. So here's my subintervals, right? So notice how the 2 just comes down. The 2.1 goes in 2 different places. The 3 goes to 2 different places, etc., all the way to 5. And you do the same with 2, 3, 4, 5. So now think about this for 1 second. Which one is regular? So obviously the second one is regular. And why? It's because each of these intervals are the same length. Here we have a length of 1, 1, 1. On the top, they're all different, right? Here is 0.1, here is 0.01, this one is 0.3. So each one has a different length of interval. And so what we're going to mainly do, so let's, so here, actually, do one by yourself. Start off with A is equal to 0, B is equal to 1. And try to come up with a regular partition yourself. So I want you to give me a regular partition. Not just any, a regular one. So hopefully you paused and you tried. And there's 1.5 million examples. So you could just do the easy one, that you can cut it into tenths or fourths. You can cut it into thirds, right? You can even just keep it like this. This is also a regular partition. So these are all different ways of doing this. And so we're going to call, so since we're mainly going to be dealing with regular, so we're always assuming regular, right? Maybe I should highlight this. Always assume regular. And so what we're going to do is when we have regular intervals, right, they're all going to have the same length. So we're going to define what this length is, and that's just going to be this difference, right? And this we've seen a few times is delta xi. This is just xi minus 1. And this is given by this interval, right? So this is our change in x, right? So when we had like a change in x, we had something like this. And so now we're ready to define our summations for our little areas. And basically what we're going to do is we're going to define what's called the Riemann sum. And the Riemann sum is basically saying if I have an interval AB, right, we're going to look at the regular interval xi minus 1 to xi, and we're going to take some random number inside of this interval, right? So just some arbitrary number, and we're going to define our summation as I is equal to 1 to n of f of xi star delta xi, right? These delta xi, remember, they're all the same. So really, this is exactly like we had been talking about before, right? So this is some function, right, with delta x. And so if we have, I should have drawn the same function. So let's draw here 1, 2, 3, 1, 2, 3, 1, 2, 3. So if I have the same function in all of them, we'll do this in all of them, 1, 2, 3, and let's look at some examples. One, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. 2, 3. So I drew the same graph in all of them, and we're going to look at different Riemann sums, right? Because our Riemann sum is dependent on this xi we choose. So here, if I look at, so here we'll do the left. Here we'll do right hand. This one will do middle. And this will do random. So what we'll do is we'll break it up into every one, I guess. So here, the left, we'll start off here, and we'll draw this rectangle. I should have, okay, we're actually going to just pretend they're above the zeros. So we're going to cut here, because we haven't really talked about negatives. Ta-da! Look at that. Erasers are amazing. Okay, cool. So we'll cut off at 1 or minus 1, 2, 0, 1, 2, yeah. So we'll cut off here. That's one of them. So here the left-hand side, right, we always grab from the left. Here we grab this rectangle. And then this is this rectangle. And then this one is this rectangle. Right? So this is one way. So this is where our xi star is equal to xi minus 1, right? It's the left-hand side. This is xi minus 1, xi minus 1, here's xi. So the right-hand side is going to be different, right? So this one is going to be when our xi star is equal to xi. So it will grab from the right-hand side instead. So notice how here we do, I guess, yeah. This is not a, this should go all the way. Sorry. I guess maybe we'll make our intervals here. That's it. So our interval is between minus 2 and 2, I guess. So here we're doing interval minus 2, 2. I'll put that there so I remember. So here we start off with 2, and we draw one little rectangle. And then here we have the right-hand side gives us the second rectangle. Here the right-hand side gives us a third rectangle. Right-hand side gives us a fourth rectangle. And that's it, right? So we went from positive 2 to 2. And here we have xi star is equal to xi. How about if we were to take the middle of each interval? Right? So here I take this middle part and I make this be my interval. So I take the middle, and then I take that to be my rectangle. And I take this to be my middle, and I take that to be my rectangle. I take this to be my middle. So here, this point is in between 1 and 2. And I draw a rectangle where my width, my height is that, and my width is my interval width, right? So this is how I'm calculating it. And then random, so here's my things. So for each one, I'll choose a random point. I'll do one here, so here's one. We'll do this one, so here's another. I have to go through. And then we'll do this point. And then we'll do this point, I guess. So here, this was random, right? So notice how each graph, so here the xi star is equal to xi minus 1 divided by 2. Did I do that right? Yeah. And so we have these. And so we actually have names for these. The right-hand sum is the Riemann sum where we set xi equal to xi, right? So we did this already up here. Similarly, we can do the same thing with left-hand side. The left-hand sum is the Riemann sum where we're letting xi star be the left-hand thing. So here we have this in the top left. The midpoint one, the midpoint sum, is just a midpoint sum where we let xi star equal to xi minus 1 plus xi over 2. So we have that here. And so what we're going to have, but what we really want, so the big thing we want, but what we really want is to find exact. And maybe I should, let me undo this. I don't want all this. I just want exact. But we're trying to find exact area. And how do we find the exact area? We find it by, how long has it been? Yeah. We find it by actually taking limits, right? So what do we want to do? And we'll do I want to? Yeah, I'll go over this now. And then we'll re-go over it on Friday. So basically what I want to do for these is notice how if I were to shrink, if I were to shrink these intervals, so here, let me choose a different color. If I, we'll do green. If I take these intervals and I make them smaller and smaller, so if I were to do even smaller, where do I want to draw this? I'll draw it here. Here, so if I make this big, so if I make these intervals even smaller, right? Notice how I'll have even less error. If I make them even smaller, the error just gets smaller and smaller and smaller until I kind of fill in everything. And so what I want to do is I want to make this change. So I want to make these delta xi go to 0, right? I want to make this interval go to 0, become 0. And this should look familiar, right? This should make you think of limits. And that's actually what we're going to want to do. We're going to want to use limits in order to solve these. Yes, we are going to use limits. It sucks, but this is what it is. And so basically what we're going to want to do is we're going to want to find the limit. So here, let's first draw our normal Riemann sum. So here we have I is equal to 1 to n of f of xi I star. Remember, the star doesn't really mean anything. It's just saying choose a point. Delta xi. And my delta xi, I'm making it go to 0. So another way to write this is that I want this n to go to infinity. Because if we have an infinite number of points between these two, right? So if I have an infinite number of points between A and B, then the distance between any two is going to get smaller and smaller, and this is going to go to 0. And this is what we call Riemann integrable. I need blue. We call this Riemann integrable. And we'll talk about this a little more later. But for now, this is the general idea of integration. We want to take these summations and we want to make them so small that, that our interval length is going to 0. And so we'll stop here for today because I think that's more than enough. Yeah, that's more than enough. We'll stop here for today. And we'll talk about integration starting on Friday. Yeah. Have a fabulous Wednesday, and I'll see you all later. Or talk to you all later. Bye.